Okay, so in this video what I'm going to do is use the principles of what we've learned on convolution to bring back to Laplace and apply this to Laplace and to see why convolution is so incredibly useful for solving inverse Laplace transforms that are very difficult to solve. So let's have a look at an example. So here we have a question asking for the inverse Laplace transform of 1 on s squared times s minus 3. Now normally what we could do is just use partial fractions as we've done before, but let's say that you don't want to, or that it's too difficult to split into partial fractions, or you just want to find another way of solving a product of inverse Laplace transforms. It's very difficult to solve. So we said previously that the Laplace transform of f of t times the Laplace transform of g of t equals, rather does not equal, the Laplace transform of f of t times g of t. Rather, the Laplace transform of f of t times the Laplace transform of g of t is the Laplace transform of the convolution of those two functions, of f of t convolved with g of t. So, if we take the Laplace transform of f of t as f of s dot the Laplace transform of g of t, which is abbreviated as g of s, we can say that that is equal to the Laplace transform of the convolution of f of t convolved with g of t. Yeah? Now, if we take the inverse Laplace transform of the left-hand side, that's going to be equal to the inverse Laplace transform of the right-hand side. And the inverse Laplace transform over the Laplace transform cancels Laplacian operations, so we're just going to be left with the convolution of f of t and g of t on the right-hand side. So the right-hand side, we're just going to be left with f of t convolved with g of t. And on the right-hand side, we're going to have the inverse Laplace transform of f of s dot g of s. And this is the magic bullet when it comes to inverse Laplace transforms that are very difficult to solve, because what we can do is that we can say that any product is f of s, and then the other product, we can call it g of s. Then if we find the inverse Laplace transform of f of s, which is f of t, and the inverse Laplace transform of g of s, g of t, we convolve f of t and g of t, and we'll get the inverse Laplace transform of those two products, of f of s and g of s. So over here, we have 1 on s squared s minus 3. So let's go ahead and rewrite that as the inverse Laplace transform of 1 on s squared dot 1 on s minus 3. And we can let f of s equal 1 on s squared, and g of s can let g of s equal 1 on s minus 3. Now, that implies that f of t, I'm taking the inverse Laplace transform of 1 on s squared, is going to equal t. Yeah? Why? Because the forward Laplace transform of t to the n equals n factorial on s to the n plus 1. So if t to the power of 1 is going to be 1 on s to the 1 plus 1, 1 on s squared, which is what we have here, so I know that the f of t equals t. And from here, if g of s is 1 on s to the minus 3, I can say that g of t is going to equal e to the 3t. Yeah? Because the Laplace transform of e to the at equals 1 on s minus a. Yeah? So again, that's why it's really important to be very good at this normal forward Laplace transform, so you can recognize what the reverse ones are. So we have f of t is t, and g of t is e to the 3t. So therefore we can say that the inverse Laplace transform of 1 on s squared dot 1 on s minus 3 is going to be equal to t convolved with e to the 3t. So all we need to do is find the convolution of t and e to the 3t, and we should have the answer. So now we need to know what t convolved with e to the 3t is. So we can say that the convolution is going to be between tau equals minus infinity and tau equals positive infinity, of f of tau dot g of minus tau, minus tau plus t, d tau. Yeah, simple as that. So if f of t is t and g of t is e to the 3t, we can say that f of tau is going to be tau, and we can say that g of tau is going to be e to the 3 tau. Yeah? So we can say that this is going to be equal to between tau equals infinity and tau equals minus infinity of f of tau, which is tau, dot g of t minus tau. Well, if g of tau is e to the 3 tau, e to the 3 t minus tau. Yeah? Is that correct? Yeah, that looks good. D tau. Yeah, because if that was g of t, it would just be e to the 3t, and then you just replace t with t minus tau, whatever the argument is. So yeah, that's fine. So let's proceed with this integration. Okay, so I've got to this point here. I've taken e to the 3t out of the integral, and we've got tau dot e to the minus 3 tau d tau. So at this stage, I'm going to use integration by parts. Just one very important side note is that we changed the limits from positive infinity and negative infinity. When we said f of tau, g of minus tau plus t d tau, to, we cross that out, we put 0 there, and we put t over here. Tau equals 0 and t. So why did we do that? Sorry. So how could we change the limits just like that? Well, the reason we could do that is because let's take any function. Let's take gt minus tau. When t minus tau, which is describing the domain on tau over here, when that is less than 0, we can say that the function of g is going to be 0. T minus tau is less than 0. When this function, when the argument is less than 0, meaning when we're talking about what's happening over here kind of thing, it's all going to be 0, isn't it? Because the Laplace transform is always for t greater than 0. So when t minus tau is less than 0, we can say the function is going to be 0, meaning that it has to be greater than that. And at this point, we can say that tau is greater than t. So it has to be greater than that point. So we can say that the absolute maximum value of tau has to be t. Why? Because when tau is greater than t, we're looking at the function in the domain which is defined to be 0 according to Laplace over here in this section over here. So that's why the maximum value of tau can only be t, because if we take the argument over here, when tau is greater than t, we're looking at g of a negative value over here, and g of a negative space over here is going to be 0 because Laplace is defined between positive infinity and 0.